Are you recording now, Mike?
Yes, we're being recorded.
Okay.
Oh dear. Okay. So this is really part one of part one because I had this broken down into three presentations. So this is going to basically cover everything. I've got quite a bit of material, and we've got.
Daland.
Can you hear me?
They're up here.
Yeah, but Daland is. Yeah, I can hear you. Someone else is on. Has their speaker on?
Yeah, I can hear somebody else talking. I don't know. Anyway, so the premise is going to be model railroad signaling and what it is, how it works, and how it relates to model railroads. So with that, we'll kind of get into it. Why would we want to do this? Well, for one, it's animation, and it's more than just the trains moving. It's sort of what I call a static dynamic interface, if you will. It's things that don't necessarily move, but have some form of change to them. That being signals. It improves prototype fidelity, and it creates and enhances operations that are based on prototypical operations, if that's your thing. You do gain a lot of experience in electronics, computers, and logic-based systems. So with that said, if you're not comfortable with computers, the internet, electricity, electronics, user manuals, and things like that, this might be a little out of your league. So I know it's not for everybody, but I'll try to make it as simplistic as I can, and hopefully I don't scare anybody. We'll just go over the history of railroad signaling, the basics of what railroad signaling is, and the differences in how in the model world we can implement them. How prototype signaling relates to model railroads, and how we can utilize some of their functionality to mimic in our modeling schemes. There's various signal implementations and what those trade-offs are given those implementations. So going back, railroad signaling got its very first iteration back in the 1880s. Simple block signals came online, and they usually were just tidal signals. It was fairly primitive. They were all relay driven, along with other means to detect, calculate, and display signal aspects to the train crews. So you'd either have a light that would turn on or something like that. And until the advent of reliable microprocessors, the signaling architecture and the way that the railroads implemented it really didn't change much. There was no, if your hardware that was 50 years old was still functional and you could get parts for it and it would work, there was really no financial incentive to go and change that. So, but what we find is that, and I've done a number of implementations now. Usually, the cheaper and the less prototypical you get in standard, the cheaper, more simplified wiring, less hardware you have to invest in. But that does come along with disadvantages in that your signals are not going to show as much. Your changes typically are going to require some type of rewire. And your implementations will not show something that you go out in the world and be able to see. They're not prototypical. Getting more into the prototypical standards, if you want a full-blown CTC system like Lee Nicholas or Gary Peterson has, they are more accurate. They're easily customizable, easy to expand, but they do come with higher costs. And fortunately, they can usually require interfacing to a computer, and that usually scares a lot of people off that may not have that background. And of course, some people just don't get it. As I've found out, you really can do this, and they say, oh, that looks nice, and they go off to do something else. So really, this is just kind of a very simplistic idea. Switch point indication would be something like simply wiring up a light to your switch motor. It simply just flips direction. You'd never see that done out in the prototype world. It just doesn't exist. There's usually something else that's behind that the railroads want. You may get that in a yard, but it's not considered signaling. It's just showing an indication of which way the switch is thrown. Occupancy, you get into occupancy detectors, then you get into ABS, which is the signal operates on its own. It doesn't have any human interfacing. It just simply detects based on switch point position and block detection of where there's a train. There's commercially available circuits out there that will do things. You hook it up and it may do some signaling behavior or whatnot. But then, of course, to get into the full line of computer interfaced control systems, that will give you turnout control, position feedback, signal control, and so forth. This is just a really simple diagram of turnout point position. As you can see, it only does two things. It'll display on the standard route, and then the one to the right is a diverging route. So it simply just gives two indications, and it has no feedback or control based on occupancy. It blocks ahead. So again, this is easily accomplished simply wiring up two signals, power routed through the contacts of the tortoise. It is simple, but it's not considered a prototypical implementation. If this is all you want to do, there are circuits out there that you can build. They're fairly simple, and they do whatever. However, again, they're not prototypical. So let's talk a little bit about something that usually comes in line with signaling, what we call rules of the road, or better, track authority or track occupancy authority. These are types of organizing systems whereby trains have authority either by paper or by a timetable seniority or superiority or something like that. And there are a number of systems out there. You have paper rule books, verbal forms of authority, track warrant control, timetable and train order. These are systems that were used back in the day where they didn't have a radio to communicate with crews on the trains. And so the paperwork was basically your authority, and you knew where you could go from point A to point B. And then along comes CTC, Centralized Traffic Control, which was a signal system, but it also did something unique in that it conveyed the authority that these prior systems, track warrant, timetable, and train order did. It conveyed the authority through the use of signals. Prior to that, other types of systems out there, signal systems, did not convey authority to the trains to occupy a track. You had to have a piece of paper or a radio communication that you recorded down on paper and read back verbatim that would give you that authority. And the signal system was there simply as an additional means of protection to prevent mishaps, trains running into each other, and so forth. So the three types of systems that most signals fall under are automatic block signal, APB, which is absolute permissive block, or CTC, centralized traffic control. And an automatic block signal system is just a series of consecutive blocks. And I've got a demo, by the way, at the end of the by the end of the clinic that I'll show you. It's a series of consecutive blocks governed by block signals, cab signals, or both. And they're actuated by train or engine or by certain conditions affecting the use of a block, i.e. an open switch or a broken rail. So it's just an automatic system. It has no interfacing to a dispatch center. There's no dispatcher that can change the signals or make a signal go, to green or upgrade or anything like that. It simply just responds to field conditions. And as you can see here, this is a very simple representation. If we look at the signals going from left to right, we'll see that at the top line there, we have all green signals. And we have a train come onto the first block, but it's behind the signal, so it sees the first signal is green. As soon as it passes that signal, then that signal goes red because the block ahead of it is occupied. And then as we start going down the line here, you'll see that the signals start to cadence with a yellow, and you can't see it on the second to last line. The very first signal there is a flashing, we consider that a flashing yellow. So we have green, red, yellow, and flashing yellow, and then to green on the last line. So that's just a simple implementation as the train progresses down the track. Absolute permissive block system is an ABS system in sorts for single track railroads configured to automatically provide absolute signal protection between opposing trains on a single track and at passing sidings, but allowing following trains to proceed governed by permissive signals. Basically, all this is saying is that in the case of ABS, because of the way the blocks are laid out, we don't have the ability to oppose trains that are going in opposite directions head onto each other, that they would have a protection block in between because of the cadencing. Absolute permissive block solved that problem by basically placing what we call a stick, that once the train goes onto the single track, all trains in the opposite direction, whichever one hit first, all signals in the opposite direction will drop red. So, 3 or 4 block signals down the line in the opposite direction, that a train going in, let's say in this case, an eastbound, the westbound train would see a red signal, but the eastbound train, because you got into the block first, would see it, a series of permissive signals. The other train would not, and it's all automatic by that case. But there's documentation out there, and I'm probably confusing without having the ability to display this. But in any case, if you go and look up absolute permissive block, there's a lot of material out on the internet that will showcase how these systems run. But again, when we get into ABS and APB, we have automatic block systems and absolute permissive block systems that require track or occupancy authority. In other words, signals do not convey authority to occupy that given set of track. Again, examples of track occupancy authority: timetable and train order, track warrant control, direct traffic control. And again, these systems, these track authority systems, they convey authority to trains to occupy the main line or branches via radio communications, written authority via agent, orders picked up in a station or yard office, or the superiority of trains based on timetables. So we're kind of bridging that gap between between signal systems and authority, but the two are essentially they're mutually inclusive of each other in certain cases. Centralized traffic control, again, is different. Is a term used to describe a system that allows remote control of a signal system. CTCs allows a single dispatcher to directly control and monitor a long section of railroad, often a whole subdivision. Provides the greatest traffic capacity for a line, as the person with the traffic overview is also the person directly controlling the traffic. So, and it is or was a trademark name for the control system built by Union Switch and Signal. And then there was another company, General Railway, used a different name, and their system was incompatible with US&S, but they both did the same function. So it's kind of like Mac versus Windows. They both did the same thing. There are certain similarities, but you can't run Windows on a Mac, or at least historically you couldn't, and vice versa. So here we go. This is an image. This is the Nicholas's CTC machine. I've operated this machine many times. It's an absolute blast. I'd rather be doing this than actually running trains. So I've really had a very good time on that. It looks complicated, but once you understand the fundamentals and you kind of get to know the railroad, it's an absolute blast to run. This is Gary Peterson's modern day version of CTC. It's all click and point, mouse driven. It has all the interlocking of the other machine, but it's all done through computer. You have the ability to click trains and be able to track. And it's this is CATS. This runs underneath JMRI, so it is a JMRI. It is a JMRI application. So let's talk a little bit about interfacing hardware. Inputs and outputs devices. What are input and output devices? They are inputs are variables, track circuit detectors, switch position, fascia controls, computer peripheral devices going into a computer, CTC machine controls, contacts. All of these things are inputs coming in. We're telling the system something. And also the ability to put DCC throttle accessory commands. We'll talk a little bit about that later. An input is any information in binary form, ones and zeros. That's how computers communicate. That is used in calculating a logic conditional statement and ultimately resulting in an output, some sort of output state. Logic is predetermined set of rules and statements that determine a result after the calculation of variables. So again, we have an input to variable. We have a logic, which is an expression, usually mathematical. This and this equals this, or this and this. If not, then do this. those types of things, a lot of if statements. And then, of course, our output is the result. Outputs, signals, switch motors, remote panel lamps, accessory devices, CTC machine indicators, things like that. Those are all types of output devices, things that we're controlling once the calculation is made. And this all applies to the prototype as well. There's many manufacturers out there that have systems already built that you can buy, but again, they're kind of canned, so you really can't go in and make a lot of changes to them. You can do your own, do it yourself. There's a good website there, circuitus.ca, Circuit Index, if you want to screen capture that. They also have circuits in there that you can build, like traffic signals, traffic lights for an intersection for automobiles and things like that. There's a lot of good stuff on that website. There's computer microprocessor interfaces, LCC, OpenLCB, NMRA-NET. That's a big one that's coming online that the NMRA's kind of pushed. It's a good system. CMRI, that's the system I'm most familiar with, Bruce Chubbs' system. It's a hybrid do-it-yourself. There's a couple of things you have to buy from him, but the vast majority of it is all open sourced and all open code. Digitrax has their system, and NCE has some hardware, but I haven't played with any of that. They're usually easy to install. They're reasonably accurate signal disciplines, although not always. They may require many circuit board purchases to make the signal system work the way you want, and they don't always lead to a very easy reconfiguration. So you may either have to buy something that's specific to the task that you need, or you're just going to have to accept what they're willing to offer is what you're going to have if that's the route you want to go. And this is, again, all getting a system that does not require any interfacing to a computer. Do it yourself, you get more customization, but it can require a lot of wiring and components for a complex signal system. I've seen some systems out there where people have done that, and it's very, very, very complex. It takes a lot of time to wire up. You're going to get to know the underside of your layout very well. And you need a very good understanding of electronics. It's not a matter of if you will need to troubleshoot it. It's going to be a matter of when. And that's speaking for experience on all of the systems out there. Computer microprocessor interfaces. Those types of systems, CMRI, OpenLCB, Digitrax, they're very good systems, but they usually have the highest financial investment of all the three main options. They almost always require a computer. OpenLCB is kind of getting to a point where that may not necessarily be the case, although I haven't played with it much, but in reading its documentation, I'm seeing that they're now getting it to where these devices will talk with each other. You need to know how to program it, or at least know somebody who does. And changes in track layout, signal place, and whatnot are easily made in software. Minimal layout wiring changes needed in most cases. So it does have an advantage of having that situation. Signal systems usually boil down to Boolean logic. If A block is clear and B block is occupied, then light yellow signal. That's what I was mentioning earlier. Timing, wait X minutes and then do something, so you can get a computer to do that. So from this point forward, I'll be focusing primarily on implementation and use of the Computer Model Railroad Interface, CMRI, by Dr. Bruce Chubb. And there's a number of reasons I feel the system is superior to other systems. It's open source with only one proprietary component of the system, and that is the what we call the U1 microprocessor chip on the cards. There are other systems being built to work with the standard CMRI net, and there's a couple of other systems out there that are compatible with this. Cost-effective implementation. It's very inexpensive compared to other systems out there based on your per IO interface requirements. You can get down to about $1. It's gone up just a little bit, but basically down to about $1 on what we call the S Mini card. per I/O. So it's fairly cost savvy. Peripheral devices may be of one's own choosing, provided the logic levels and states match the I/O requirements of the CMRI system. You buy the hardware however you interface it, as long as you maintain what we call traditional logic or TTL logic levels, you'll be fine. And it can be operated with a myriad of different software programming approaches: BASIC, JMRI, Visual Basic, C++, C++, C#, Python, etc. All those systems are out there. I do recommend that if you're at all interested in that, go to the jlcenterprises.net website and purchase these books. Even if you're not going to be building a signal system with this hardware, the documentation out of the handbook is handbooks volume 1 and 2 will give you a very good insight into the signal systems, the prototypes, and how they operate. Again, why do we use this? Well, the software is usually cheap or free. You can pick up JMRI for free off the internet. C#, some of those iterations out there are free, and various Visual Basic out on the internet from Microsoft is usually free. And no, I am not a programmer. So this kind of shows you a little bit of an interfacing, how you would do something on a typical layout. Over here on the, if I can get this thing to show up here, pointer options. Over here on the left-hand side of the screen is a set of outputs. This is called output connector 1, output connector 0, and then output connector 1 here. So we have a total of 48 outputs. The 24 down here on the bottom are not currently used. But we have a signal here, we have a turnout motor here, and we have a lamp here. Those are outputs. We also have inputs coming in from ECC detectors that are hooked up to the track. And we have a turnout contact closure, and we have a panel switch here. So that kind of gives you an understanding of what is an input and what is an output. Okay. So this kind of shows an implementation of how the system would be networked. You have a computer running old basic serial RS-232, maybe a USB to serial converter, and then all the cards daisy chain. And each of these cards here, this is an S-Mini on node 0, which is 24 inputs and 48 outputs. And then down at node 2, we have an SUSIC, and that one is more customizable. You can have up to 64 I/O cards in any configuration you want, up to 2,048 I/O lines per node. So you can get into the hundreds of thousands of total I/Os. Just communication on the serial side of things. Serial is standard, although we don't see a lot of serial connectors on the internet or on computers these days, but you can get converters for them off the internet. Amazon has some. This is an S-Mini card, just blown up a little bit. Again, over on the right-hand side, we have 24 outputs here, 24 outputs here, and 24 inputs here. So a total of 48 outputs and 24 inputs. The communication is handled here through what we call RS-485, and then we have power, 5 volts here, and ground. So what are inputs and outputs? Let's look at a block concept diagram. We basically we begin what we call a real-time loop. We read our inputs from the railroad. We then go to the logic portion of the program to calculate the outputs based upon inputs, signal aspects, turnout position, panel displays, etc. And then we write those to the system. This happens very fast as far as us humans are concerned. This is happening hundreds of times a second. The system is going out there reading and whatnot. So effectively, we see it as happening more or less instantaneously, but the computer is having to do some calculations. We have different types of inputs. We have a contact closure on a switch contact. We have a multi-panel switch if we want to with multiple inputs. And we also have a transistor where we can have a transistor from another device that that comes in and basically shunts that to ground. That's typically a detector. Whoops. So this over on the left on A is the method used for local control, point position, stopping block, things like that. If you have a button that you need to activate something, over on C, that's a simple but typical example of a detector output on CMRI. Outputs, we have a lamp here on A. Your signals on B is your most common method. And again, you have a relay controlled on C, which is a high current. These are just options out there. This isn't necessarily something you have to do. The signal system has to know if something's on the track. We need to have a way to tell the system that there's a train on a given section of track. This is called track detection. And there's two forms of that, optical and current. So here's a simple representation. As I mentioned before, we have a battery down on the lower left-hand side here, and we have power being fed through the rails. We have an insulated gap here, comes over and controls this relay. If we go to the next slide, you can see that a train wheel has come in here, shunted that. It's now preventing power from coming in. We would have some resistance in series with this battery, but now it has allowed that relay to drop, and now the signal is displaying red. So optical detection, it's easy to implement, doesn't require any connections with the track wiring, but it's point detecting. In other words, it doesn't detect a wide area, and it isn't prototypical. You can do point detection with optical, but it's not something that I would necessarily recommend. Be used in limited cases where point detection is required, and those instances shouldn't tie into vital operation of the signal system. Again, they're influenced by light, arm dust, wayward cats, whatever. So they can be finicky, and there's a lot of resources out there. I prefer to avoid them, and I won't be covering them any further. So current detection, that mimics the prototypical block detection, as I showed a couple slides before. And when used with transformer detectors and DCC, no direct connections with the track power are required. They require wiring tracks and track feeders into blocks. Rolling stock usually requires some kind of a resistance to pull a current but not overload the system. So you don't want to just jumper your wheels across with a straight wire. You'd be pulling too much current, but a resistor of about 10,000 ohms usually works out pretty well. Prototype operations use track circuit detection methods, so we're doing exactly what the prototype does. I won't be covering DC. I don't have a lot of experience with it these days, with DCC being the case as far as why do I need to go back to block wiring with DCC? I thought the whole point was to get away from block wiring. Well, let's look at why we have to do that. If we show here a traditional system with no signal system in place, we have, our cabs, our command station, a computer. Sometimes you want to hook it up in a programming track. But then we have power coming down, and we have the boosters going down and feeding the various block sections for circuit breakers. And we think, well, that's all we necessarily need. Well, not exactly. Even though we block it down into, we have a rail, S-rail track bus here, an N-rail track bus, and we have all these drop feeders, we're still dealing with one block. So we have to detect trains from one block to another, and we're discussing DCC track power exclusively. So here we have detectors on the lower section here, but we've now insulated gaps between the boosters. We've also put in block gaps here on the one side rail, and these detectors now can tell when something is in this block versus this block versus this block. They utilize usually a form of transformer coupling. We're basically utilizing a loop of wire around a transformer to create a little current into a detector that tells it, hey, there's something there. These all have an advantage because we have no drop through diodes. Typical silicon diode drops at about 0.7 volts. So from going from a detected section to a non-detected section, you can notice it speed up or slow down depending upon which one you're entering and leaving. You have total track power isolation, so you have no commonality between the systems, and you have virtually no loss of the system, and also no noise. So let's look at some detectors. This is a detector diagram that I saw from a presentation I did elsewhere. It utilizes some BD20s. They're NCE made. You can buy them commercially available, and they'll work just fine. They're going into an AIU for NCE if that's your system that you want to use, but again, you can use them with anything. You have your booster coming in here, going to your main line, and notice they're broken on the top side, but the bottom side is unbroken because you don't need to break both sides. This is Bruce Chubb's optimized detector. It's a little hard to see because the drawing wasn't very good, but we have a transformer right there with a loop of wire. And then this goes to a header board here. So there's the transformer right there. A comparator circuit with an adjustment control. You put power, track power coming in here, and then one side of the track comes off these screws. They're up here near the top. So you can put maybe 10 detectors on this board and detect 10 section or 10 blocks on your layout. This is a detector that I used on Gary Peterson's, built by Wayne Roderick out of Idaho on his Teton short line. It's a very good detector system. I've used it. The transformer coils are no longer available from Janeco, but I have found another source for them. But I wasn't able to get that data by the time of this clinic. So this kind of shows you, this is Gary Peterson's SLS railroad, Salt Lake Southern. It just kind of shows you where all the detectors are on the layout. Each of these gray and yellow circles right here are track detectors. So you have a lot of track detectors on the layout, but they will show where the train is at any given point in time, or if you have any equipment on the track. The signals will then respond to that based on what the computer tells them to do. There's another blown up diagram here, just kind of showing what a small section of track, what you would have for signals and block detectors. When you're doing turnouts, all switches can work with detection. A little pre-planning can make a real big difference. And when you're going to be doing that, you also want to kind of do a straight line diagram to figure out where your switches are going, whether they're going to stay in occupied territory or whether they're going to be going into undetected territory. So switches and the areas around them are typically associated with signal placement. They're called OSs and CTC territories. So you'll hear that term thrown around a little bit. Just an example of a non-powered turnout or non-powered frog turnout. We have no power going to the turnout there. So within the confines of the turnout and what we would be wanting to protect, signals would be placed here. We simply bring our power up, our detector coil comes up and powers the sections of track that we need to determine whether or not there's something within those areas. If we have a DCC-friendly powered frog turnout, we have the contacts come through. This is a common way of wiring them up, but our detector coil comes in and goes to the side when it would be thrown to the red rail so that we would be able to have continual detection all the way through it. If we're doing a common point power where your point rails stay the same polarity, this is considered a non-DCC friendly, then we have to do the same arrangement here, but just a little bit of a different configuration with regards to the frog. And anybody who's ever played with frog juicers out there, the frog juicer, because it's an active circuit, will drop power. So for the frog juicer, we bypass it and we do not put its power through the detector coil. We bring it on before the detector coil, and the small portion of the frog is not considered detection or detected. So in that case, with the frog juicer, we simply just say, okay, either side of it is detected, but the frog juicer section itself is not. But then the frog juicer will flip that back and forth, and there's a Tam Valley frog juicer for anybody that's played with them. They're pretty unique and pretty cool devices. If you want powered frogs and you don't want to have to worry about running the power through a set of tortoise contacts, I definitely recommend these. So let's really quick talk about signals. There's many different styles out there depending upon your prototype, back east, color position lights, or position signals, depending upon if you were Pennsy or Chesapeake and Ohio, different signal systems. Down in the Norfolk and Western, Norfolk Southern, they used what they called cat's eyes and whatnot. But there's a whole mess of them out there. Try to mimic an era and prototype and stick with it. There's for anybody that's been to the train shows, they've seen Richard Pachula with his little display there. He makes signals. He makes also a system that controls them, but I just prefer to use the signals. You've got a number of NJ Supply, I think it is, and Signal Logic. There's a number of different ones out there. You can also do semaphores. They can be operated with the tortoise motor, but the mechanical interfacing is the challenge, and that I've never seen wanting to get into. And the wiring of the motor is different than that of a turnout motor. Well, you have to make the turnout motor or the motor work that drives the semaphore. So here's some signal types. You've got over here, you've got this one. This is color light with a lunar at the bottom. This is a searchlight, position light with all the same colors. A tricolor, we call these typically cat faces, a color light, and of course here's the upper quadrant semaphore signal. So all these different types can be programmed or can be utilized. It just depends upon what your operation is. Again, this is more getting into a 3-color light and how you would wire it up, just different iterations. These two here are the ones that I utilize the most to make them work when I've programmed on 2 layouts here in the Salt Lake area. You can do bipolar LEDs. They will work, although I don't particularly care for the color, discrete LEDs in the signal head. But if you have some older, I remember the name of the company, Oregon Rail Supply, they did bipolar LEDs, and you can utilize these. That's what Gary Peterson uses on his. A little hard sometimes, depending upon if your color perception is exact, and mine's, it tends to be a little off. You can utilize 3-pin LEDs as well on those. You have to do a little bit of an additional circuit to make them work. Again, they'll drive anything. LEDs, incandescents. I don't recommend incandescent signals. I think Model Power is the only one. Them or Bachmann still make some. They're cheap. Then you have to replace them if they burn out. I just don't recommend them. LEDs seem to be the predominance in the industry now. If you want to do a tortoise control, this is a very simple circuit with 3 resistors and a transistor to control them. The circuit's not terribly efficient. In other words, it burns a little bit of power, but if you're running off a standard power supply and you're not really concerned about having some warm resistors. When I say warm, I do mean that warm, not hot. Then the circuit works. Otherwise, if you want to get into more complex circuits out there, you can find solid state circuits that will do that much more elegantly. So let's just take a look at signal implementation real quick. As I showed earlier, we have a block cadence from left to right there. But basically, what that looks like in code is signal 1. If block 2 equals occupied, then signal equals red. Skip the rest of it and go to signal 2. Otherwise, if signal 2 equals red, then signal 1 equals yellow, else signal 1 equals green. This is a simple ABS formulaic logic rendition going down through the cadencing of the signals that I'll show later on. But this is essentially all that the system is doing. So for a very simplistic system, you can program 4 signals in that amount of code, and it's very simple. So again, anything is possible in programming, provided you have adequate hardware resources, inputs and outputs, you understand what it is that you're after, you have the ability to write or obtain the necessary programming code, and you have the ability to understand what the system is doing, when it's working right, and when it's not. So I recommend giving it a try if you're going through JMRI, or if you're whiz on C++ or C# or Python or whichever. If you're not interested in doing programming, find something who you trust to do your programming. If you go this route, make sure that your programming helper has an understanding as to what the final outcome goal is. If you're not certain what your goal is, consult. I'm more than happy to do that. And make certain that your helper is willing to do whatever you want, and be willing to take, and make sure that they're willing to take suggestions, but your word is final. And don't be afraid to stop it if you don't think it's right, and so forth. Don't be afraid to be creative and bend the rules to suit your operating style. Your enjoyment will depend on, but don't get too carried away in going freelance. This is just a couple of pictures here showing various people's implementation on how they did things through JMRI. This is a panel that we were using. It's been updated since, or it's been updated since on Gary Peterson's that I built. You've got another control panel that I built, and again the CTC panel that I built for Gary's. In closing, it's a lot of fun. It takes time. It needs to be planned out. Ask for help, please. If you need to, reach out to me. My email is on the newsletter or other contact, and set goals and stick to them. It will really pay dividends. So I'm going to really quick, before we get to questions, I'm going to just go really quick to my demo, and then we'll go to questions. So here's a demo of the signals that I tried doing this a number of years ago, but basically you can see here we have a whole set of signals really packed in tight here, but each of these little circles here is a detector. And if we occupy this, showing that there's a train there, notice the signal went red. We go to the next one, and that signal goes red. Oops. Oh, come on. If we take that one off, notice the signal here is protecting this signal here, and this signal is protecting the occupancy. So as we cadence down here, you'll start to see how they'll start to re-upgrade. So you can kind of see here cadencing one to the other. So this is just a very simple ABS system in one direction that I threw together. And as you can tell, they do a cadencing of about 2 signals behind. And this is how they would protect the rear end of a train. Again, in this case, the dispatcher is not able to control, would not be able to control them. This occupancy would be happening by virtue of the train's occupancy. And when we lose that one, they all go back to clear. So with that being said, I'll throw questions open. It's not terribly easy. I wish I had more. I could show hardware and so forth. But with that being said, I'll open up for questions. Mike, I don't know if you want to open anything up, or if anybody's got any questions.
Sure. If anybody has any questions, just go to the right-hand side of the screen and click on the phone, or if you look like you're talking, I'll try to unmute you. Maybe you should stop sharing your screen, Daland, and then we'll see all of the grid of people.
Let's see. You're sharing screen. There we go. Okay, stop sharing screen. Got it. Okay. There we go.
I have a question, if you don't mind.
Sure. Go ahead.
I've got a brand new computer, and I went to connect it into my NCE so that I could use the JMRI. And it asked me if I was using USB. I said yes, but it won't recognize it. It said I'm not connected to the serial port. Well, it doesn't have a serial port. Is there any way to fix that?
Typically, in those situations, that usually requires. Well, let me back up. Did the command station have a USB connection on it?
I don't think so. I think it has the old converted a serial port, but it has a USB on the other end. It's like the connection.
So that's probably a USB converter, and
Yeah.
so that converter in the program or in your control panel settings would have the ability to go in and determine which COM port is assigned to it. And that's what JMRI is looking for the COM port, because ultimately it's a COM port that it's emulating on the output side of that converter that then communicates to the command station.
Well, I certainly don't know how to fix it, so I've gone in and tried to use the.
Sleeping, so I thought I'd wake you up.
Oh, thanks.
What I think would probably be the best thing, Blaine, is to maybe do a Skype call or something like that, and I can do a screen share, and then we can kind of take a look at that and see what goes on.
Okay.
Yeah, Blaine, if you bought a new computer, there might be drivers that you have to download.
Yeah, that as well. So,
All right. I did download the JMI program, but I can't get it to talk to the command station.
right.
USB drivers is what we're talking about.
Yeah.
So that would be, and again, that's one of those things that for every system out there, it's going to be slightly different. The advantage of the CMRI system is that you simply have to get a working serial port through whatever device you have, whatever converter you have out there. NCE is more or less kind of works the same way in that it has a serial command or a port on it, and you just have to be able to be talking to the output of a serial port on your computer. So it's probably like Mike said, you've got a serial converter, USB converter.
Okay. When I get time, I guess I'll give you a call and we can Skype and you can show me what to do. I've got a board meeting this afternoon with the region, so it won't be this afternoon.
So Daland, I have a question. I'm wiring up a bunch of BD20s and hooking them up to an AIU, and I've got the system relatively working. When I stick a locomotive in each of the zones, everything lights up appropriately. Right. But when I drop a 10K resistor wheel set on the track without being part of a stock car, I don't see it. And I'm running in an N scale where we've got a very low amperage system. It's a 5 amp system in theory, but should you be able to just drop a wheel that's got a 10K resistor on a zone, and should that flip the thing, or does it need weight on it? Or
well, it can depend, and it can depend upon how much. It can depend upon how much. What's the word I'm looking for? How much contact you have through the resistor. So your best bet is, first of all, is to go take the wheel, take the car, and put a meter between the two wheels, and actually make sure that you're looking at 10K. Sometimes that contact isn't necessarily always what it is, and just use a delicate force with your meter leads just to verify that you've got 10K. If you've got 10K, sometimes that can be a little high for some of these circuits. Most all of them out there should be able to handle, or should be able to detect 10K, but with it being a little high, sometimes it's not quite enough, and you have to drop that resistance down sometimes to about 7,500 and play with it. That's the other option is to go get some resistors between 5K and 10K, and drop a 10K with clip leads across your rail and make sure that it's actually detecting, and then that'll kind of tell you where your problem.
Yeah, these are commercial 10K wheel sets from Valley River or whatever the company is, but in N scale, trying to put resistors on an N scale wheel set's beyond my skill level.
I know it's been done. That would be my recommendation. Now, here's a question: do you have just one axle that has resistors on it, or more than one?
Well, I'm just testing it with a wheel that's not on any stock, and I was planning to put one wheel per rolling stock.
Okay. So first thing I would do is take your meter, take your ohm meter, and ohm out the two wheels. Make sure that it's actually at 10K and it's not sitting up at 25K. I would check that first, and then go. Are you in the Salt Lake area?
Yeah.
Okay, go down to Standard Supply and ask them for some 10K. Ask them for a 7.5 and ask them for a 5K resistor, and see if the 10K is not firing it off. See if a 7.5 will. And if it's not,
I've got plenty of resistors. I didn't think about just dropping a plain resistor across it and making sure that trips it. That's a great idea.
Don't drop anything less than about 5 across it. Otherwise, you're going to start to get you'll start to get a little bit of heat in that resistor. 10K is nice, and then it doesn't do that. So that's one thing that I would do. I haven't had a lot of experience with the BD20. I've got one, but I haven't really fiddled around with it, and I don't think there's any adjustment on it. Am I correct?
You're correct, but they work perfectly with a locomotive or a lighted caboose.
Right, and the reason those work well is because typically you have a decoder in there that takes substantially more current draw and a lit caboose, which is a much lower resistance. Usually a lit caboose is going to be somewhere down in about the, somewhere down in the 10 to, or somewhere in the 100 to 200 ohm range, because you got a lit caboose, or if it's an LED, you're going to be drawing about 30 milliamps. So we're with a 10K resistor across that, we're down in the 1 to 2 milliamp range, which is really, really low. Really low stuff. 30 milliamp or 20 milliamp range for an LED is considerably higher. So, does that answer your question, Mike?
Yeah, thanks very much.
Okay. Anybody else? I know it's probably a lot to digest, and once you see a system in operation, it's a lot easier to stomach. But it's a really fun thing to do to me. Even going out and watching signals on the prototype. I'll tell a really quick story about this. A friend of mine and I, a few years ago, went over Soldier Summit. We went over to Price and had dinner at a little Greek restaurant over there, and just went out for a ride and a little bit of rail fanning. We got a little bit in, but we were heading back over Soldier Summit right at dusk. And we were chasing a coal train up the hill, and I had my scanner on, and we were listening, and we were coming up just east, I'd say about maybe 3 or 4 miles east of Soldier, right of the summit, and right there the rail, the track and the road parallel each other, and there was a signal up ahead, and the train was behind us, maybe half a mile. It had stepped into the block, so the approach lit was on, and the signal wasn't green. And the crew said, "Hey, dispatcher, you said you don't have anything. You got to meet for us down in bottom of the canyon, or you got another train down the bottom of the canyon. Have you got anything ahead of us?" And he says, "No." He says, "Well, we've got we're coming up on an approach." And the dispatcher says, "Oh." And within about 5 seconds, the signal just upgraded. That type of interaction to me, and the logistics behind that is really quite fascinating to see that system out there. I mean, the signal system to me is kind of the benevolent, the benevolent king and controller of everything that goes on out there. It's the silent sentinel that just does its thing. It's a lot of fun to watch those signals do their job, and to think that there's, even though you're out in the middle of nowhere, there's something controlling that, and somebody thousands of miles away can actually see what the system is doing. So it's really a real fascinating aspect of this hobby that really does not get a lot of study, but for me is just as much as of interest to me as watching the actual trains move. So, but really, that's all I got, Jim. I'll turn it back over to you.
Okay. Can you hear me?
Yes.
Okay, great. Well, thanks, Daland, for that. It was interesting. It's definitely one of those things that probably not many of us are like right at that point where, hey, I need to do this. But it sounds like maybe Mike and Blaine are in the midst of that a little bit. But for me, it's something that, yeah, I'm interested in that. Maybe someday down the road, I'll add it into my system, and now I have a little bit of knowledge and a little bit more understanding. There were a couple things that enlightened me, so just gleaning that I think is helpful. So I'd like to thank everyone on. I think we had a pretty good group today. Um, if you haven't noticed, I've been putting the recordings up on the website under the past clinic section on that page. You can watch for better or worse. You can rewatch, or if there was something you said, "Hey, I forgot about," then you can back it up or forward, or scrub to that spot in the video.